Okay, good morning, everyone. Thanks for joining us. My name is Scott Jones, and I am currently at the Smithsonian Marine Station in Fort Pierce, Florida. And I'm joined today by Drs. Jennifer Sneed and Justin Campbell, who are currently at the Caribou Key Field Station in Belize. So they're 15 miles off the coast of Belize. And both of these marine labs, the one I'm at and the one that they're at, are part of the Museum of Natural History in Washington, D.C. During the broadcast this morning, we'd like to hear from you. So you can submit questions as we're going along. The easiest way to get in touch with us is via Twitter. So you tweet your question and just use the hashtag #CoralChat. See that there? And you can also submit questions directly via the Google Hangout platform if you're logged on and watching this with a Google account. And so with that, I'd like to introduce Drs. Jennifer Sneed and Justin Campbell. Hi, guys. How's it going?
Hi.
Can you hear me okay?
Yeah.
Okay, so if you could briefly tell our audience who you are and what you're working on and where you're at right now, I guess.
Sure. So I'm Jennifer Sneed, obviously, not Justin Campbell. We are at Caribou Bay off the coast of Belize, about 14 miles off the coast of Belize at the Smithsonian's Reefs Station here. And we are working on some different aspects of environmental factors that affect coral larval settlement.
Well, my name is Justin Campbell. I am a seagrass ecologist and coral reef ecologist. I'm primarily based at the Smithsonian Marine Station in Fort Pierce with Jenny, and we're here doing some exciting work on ocean acidification and coral larval settlement behavior.
Cool, thanks a lot. So you said ocean acidification, and when we advertised this event, we framed it as research on coral reefs in the face of climate change. And so I think a lot of folks probably aren't as familiar with the ocean acidification part of climate change as they would be as warming temperatures, especially when we're talking about coral reefs and what might happen to them as the climate changes. So could you elaborate on what ocean acidification means and how you go about studying ocean acidification?
Sure. So when we use this term of ocean acidification, it really means a slow and gradual increase in the acidity of oceanic seawater. And this term acidity is all something that we're familiar with. It's a term that we use to describe the chemical composition of a particular volume of water. So for example, when we think of something that is really acidic, something like a common item like lemon juice is extremely acidic. And then there are other items that are less acidic that we're familiar with, like baking soda or certain types of detergents or soaps. And so we can actually measure the acidity of a particular volume of water on a scale. It's called the pH scale. So something that is very acidic, like lemon juice, has a very, very low pH of around 2 or 3. And then something that's very basic or non-acidic has a pH of higher values of around 8, 9, 10. The top of the scale is at 12. So we have this scale that we can use to measure the acidity of a particular volume of water. And this is important and it's back to the oceans because oceanographers have been detecting a slow and gradual increase in the acidity of seawater over the past several hundred years. And so as biologists here, we're interested in these changes in seawater acidity and how they influence marine life. And so we use this term ocean acidification to describe these slow and gradual changes in acidity. And it's related to a broader concept of climate change, and I'll actually get into that in just a moment. However, so we can think about this process of ocean acidification, and one thing that we can do here at the Marine Station in Belize is that we can actually replicate these OA conditions. OA stands for ocean acidification, and transplant corals into various buckets and look at how they respond to these different types of conditions. So there are a lot of physical and chemical parameters that have to be just right in order for marine life to grow and thrive. So the temperature needs to be just right, as Scott mentioned earlier. The salinity needs to be just right. Oxygen levels need to be just right. And the acidity or the pH also needs to be just right. So that's what we're here doing. We're looking at how marine life responds to these changes in oceanic pH.
Cool. So I'm just going to share an image then of the lab as you set it up. I don't know if you can see that, but this is the sort of mimicked environment that you're creating. Is that correct? Could you tell us a little bit about what's in this picture?
Yes, that's right. Sure. So the way that we study how marine life responds to changes in pH and acidity is that we can essentially conduct a comparative experiment. And so that's what you see shown in the photograph. We have a series of smaller containers, otherwise 5-gallon buckets. Some of these buckets have a reduced pH, so we can artificially and precisely control the pH within certain buckets and reduce the pH down a certain level. And we can compare coral responses in those buckets to other buckets that are under control or normal oceanic pH conditions. So we saw 12 buckets in total. 6 of those buckets are of reduced pH, and then the other 6 buckets are of control or normal pH. One of the ways that we control pH is that association between pH and CO2. So as CO2 increases in the atmosphere and it increases in seawater, there are a series of chemical equations or chemical reactions that actually reduce the seawater or reduce the pH and increase the seawater acidity. So we have a computer that actually monitors the pH within each one of these buckets, and the buckets that receive increases in acidity, the computer automatically adds a little bit of CO2 and reduces the pH to the level that we're interested in.
Oh, that's cool. I didn't realize it was so automated. That's really neat. And so, okay, so what's happening?
Mm-hmm.
What's happening in these buckets? What kind of marine life is in these buckets? I know we're working on corals, so tell us a little bit more about the detail of the experiment.
Yes, so we've been trying to understand how different environmental factors will affect corals during their early life history stages. Corals, when they reproduce, they have a larval stage similar to the tadpole of a frog. They actually have a swimming stage, and that larvae can swim around and go down to the bottom, attach, and metamorphose. And we're really interested in that process of what's happening when the larvae swims down to the bottom, attaches, and metamorphoses. And we want to know how these different environmental factors, like ocean acidification, and we're also working on the presence of a lot of seaweed on the reef. So we're looking at how those factors impact the ability of these coral larvae to find a place to attach and metamorphose on the reef.
Okay, so I guess that stage in their life is really critical then to how well corals survive and react in these changing environments, I suppose, then right?
Yeah, so one of the big things that's happening right now in the Caribbean is that a lot of the coral reefs are becoming overgrown by seaweed. So we have less coral cover, more seaweed cover. And one of the major ways that that's going to be reversed is by the recruitment of new corals onto the reef. So we need to have these new baby corals be able to come onto the reef, attach, and metamorphose in order to have new corals on the reef. Otherwise, the reef's going to continue to have a lot of seaweeds. We also call them macroalgae, seaweeds, on the reef, and not as many corals. So it's a really critical step in the life cycle of the coral. And so we're trying to understand how these environmental factors were going to affect that process within the coral's life cycle.
Cool. That sounds like an interesting experiment. So how do you get the larvae? I mean, if you have adult corals like the one I just shared an image of a moment ago, how do you go about getting that coral's babies, so to speak?
Yeah. So basically, for these corals that we've been working on this month, the ones that the Parietes asteroides, it's also called the mustard hill coral that Scott just showed, we actually bring those corals into the lab. So we can go get them off the reef, we bring them into the lab, and we can put them into a bucket, this one that I have here, you can see. And what we did is actually drilled a little hole in the side of the bucket and put a piece of tubing in. And so we'll have water that flows over the coral will be in the bucket, We have water that flows over. At night, the coral will release its larvae into the water. And so those larvae then can kind of flow down the tube, and then we catch them in another container. And this container has mesh on the bottom, so we stick it inside another one, and then the water just flows through and out, but the corals get trapped in this container. The larvae get trapped in this container that has the mesh on the bottom. And in the morning, we wake up and hopefully, best case scenario, have hundreds to thousands of larvae in one of these containers.
Cool, that's neat. So you're 15 miles off the coast of Belize at a remote field station. You don't have a steady supply of electricity or a Home Depot that you could run to get some more supply. So what kind of things make working at a field station like Caribou Key different than doing an experiment at a laboratory on the mainland like Smithsonian Marine Station?
Well, yeah, sure. I think it's just for some of the points that they got. It's remote, and so we don't have the luxury of running to the store to get additional supplies. So you have to be very self-sufficient. You have to make sure that you bring all the equipment that you need for a successful project. And furthermore, it's difficult in regards to power consumption as well, as you've mentioned. So the entire station is pretty much supplied by solar energy, and so we need to be conscious of the amount of electricity that we use within our experiments. When we're working at the fields at the marine station in Fort Pierce, many of those limitations are alleviated. So you have to really think carefully about the design of your experiments, and particularly a lot of preparation needs to go into planning and packing up your equipment.
So how long have you've been down there for a week, and when are you leaving? So how long have you been down there?
We've been here for about a week and a half. We go home on Thursday.
Oh, okay.
So we'll be here for 2 weeks.
So is that, would you describe that time as, you have a lot of, you feel like you're rushed the entire time, you have to cram all that work into a short period of time, whereas when you're here in Florida, you have more the luxury of like having more time, or how do you go about dealing with that?
Well, definitely, when you're at a field station like this, you try to get as much done in the short time that you have, because you only have a couple of weeks to get as much field data as possible, then that we can take back to Florida and start, analyzing the data and writing up papers and things like that with more leisure. But here we have to try to get as much as we can done in a short time. And also, when you're working with coral larvae, the corals only reproduce for a very short time. So you have a short time frame. Sorry, we have somebody talking in the background. You only have a very short time frame to get those larvae from the corals. And so we really have to work around the schedule of the corals. Some of the corals that we work on only reproduce 1 or 2 nights a year out of the whole year. So we have to be there and their offspring to be able to use in experiments. And they're only really viable to use in experiments for maybe a week to 2 weeks. So
okay, so it's not a coincidence that you're there right now.
Yeah, on a short time scale.
Okay, so we do have a question from the audience, and this person wants a little more details about how you collect the corals for your experiments.
So for the ones that we're working on this trip, we actually go out and dive and use a hammer and chisel and pop the corals up off the bottom, so you can get an entire coral colony. We're using small colonies, maybe this big or smaller, and we'll get that whole colony up off the reef. We bring it into the lab, do the setup like I showed for getting the larvae from it, and then we can take them back and re-epoxy them down where we pick them up. So we put them back on the reef so that we're not taking corals permanently out of the ocean.
Oh, I see. And so they go back and they do pretty well after you return them.
Yeah, this is the first time that I've worked on this particular species in Belize. But when we do this work in Florida, we do a lot of this work in the Florida Keys, and we have nearly 100% survival of the corals that we put back on the reef.
Cool. So they must be pretty hardy then. So just since, you know, as scientists, they get to work in the field, work on coral reefs, could you tell us a little bit more about, you know, what you consider to be the favorite part of your job?
Justin?
Well, I can't deny this is definitely a perk of the job, being able to come here and study and work on the things that I'm interested in. So certainly the travel aspect of being a marine scientist and being able to go to places all over the Caribbean and conduct field work is something that I really value as part of my job with the Smithsonian.
Yeah, and same for me. I mean, you can't beat this view. I'm gonna actually turn the camera around and see if I can give you a shot of what we're looking at right now. I don't know how much you can see, but we're pretty much right there. Which is amazing.
Cool.
And, you know, it's, as I think marine biologists, we're really interested in the subjects that we're studying. So it's really fun to be able to come and do these experiments and get some answers and get some insight onto how things are working in the natural environment. And then we can go back and do some of the more mundane writing and asking for money and things like that when we get back to Fort Pierce.
So there's some harsh realities too. So another question we got from the audience is some more details about the experiment. So when you do these experiments with the coral colonies, do you then use the same colonies each time, or do you change it up and get different colonies from the reef?
So like I said, this is really the first time we've done it here in Belize. So obviously we're not getting colonies that we've collected before.
Sure.
But when we do these sorts of experiments down in the Florida Keys, we do a little bit of both. We have some colonies that we've tagged down in the Keys, and we monitor them year after year to see, kind of track their reproductive abilities. And then we also collect some that we've never collected before, just to kind of hedge our bets, because we don't want to end up somehow not getting larvae. So we try to keep a good mix to make sure that we get the larvae that we need for our experiments.
Oh, interesting. So there's differences between the colonies and how much they reproduce.
Absolutely, yeah. Some colonies don't release at all when we collect them. And so these guys actually can reproduce over a series of months. We usually monitor them in April, May, and June. So it could be that we collect a colony that already released back in April, and we just don't know. We don't have a way of knowing if they're going to release or not. So they may have already reproduced for the year and we don't know it. So we bring them in, I would say this time maybe, half or maybe a third to half of the colonies that we collected actually released larvae. So
oh, wow.
a good portion don't release larvae at all.
Interesting. So working on coral larvae can be a risky business then. You might have a lot of time and energy invested in a project, and if the corals don't do what you've hoped them to do, you're kind of out of luck, huh?
Yeah.
Yeah, unfortunately that's the case. It can be risky, but we're fortunate enough to at least get a couple larvae to conduct some experiments for this trip.
Yeah.
And so, and I guess going along with that same train of thought, considering that you're studying things in nature and that things are not necessarily predictable, how are things going on your trip now, and how are your experiments going?
Well,
Funny you should ask.
funny you should ask. Actually, well, we didn't get as many larvae as we'd hoped to start with. We did get enough larvae to set up this experiment in the ocean acidification system that we planned on doing. We usually like to do a few other assays while we're down here, but we didn't really have enough larvae to do any more than that.
I see.
And we had some issues with the setup itself. Mostly we think we didn't have enough flow in the tanks. So we're gonna try to readjust that for the next trip and learn from some mistakes I think that we made this time.
Sure, so you're constantly learning, I suppose, every time you're in the field.
And this is the first time we've tried to, this is the first time anybody's tried to do an ocean acidification experiment, I think, on Caribou Key. So it's definitely a learning process, and Justin, set up this system. It's working pretty well, but we just have a few adjustments to make before the next trip, and then I think we'll get it up and running the way we need to.
Yeah, no, I agree. I think the next time we come down to set up this OA system, we'll certainly have all the details worked out. So sometimes in science, there's a little bit of a trial experimental phase where you need to figure out how exactly you're going to execute your experiment and set up your design.
Yeah, I think that's a pretty interesting thing about science, and maybe field biology in particular, is that it's not as easy as you'd think, and especially maybe even your own planning can be a little oversimplified, and then you never know what's going to happen. So we do have another question from the audience. How do you know, well, I guess you sort of answered this a little bit about the timing aspect, but how do you know when corals are going to reproduce?
Well, so for several of the corals in the Caribbean, people have been kind of studying when they reproduce for a while. So with this species that we're working on this month, Phraites asteroides, we know that they will release during the new moon in April, May, and June.
Okay.
And so that's kind of when we focus our efforts. We collect them around the new moon, and we know they'll release them. There are other corals like the elkhorn and staghorn coral that we'll be working on in August that release their gametes shortly after the full moon in August. So they really are 1 month a year, one time kind of corals. So, so it depends on the coral species, but it's known for a few different coral species when they typically release their larvae or their gametes.
And then a similar question from the audience as well is, do they only release larvae at night, or do you sometimes see them during the day?
Most corals that I know of release larvae at night. So there are two different kinds of reproductive strategies for corals. They can release fully developed larvae, and we call those brooders. That's like the one we're working on this month. And we have others that are called spawners that release gametes, so eggs and sperm, into the water column. Those eggs and sperm float up to the top, and then they mix at the surface, and fertilization happens there. And then larvae develop from those fertilized eggs. So most of the corals that I know of release either larvae or gametes at night. There is one that I recently found out about, the Diploria labyrinthiformis, that releases actually before sunset. So that's a little bit of a different strategy, but it actually releases during the day. And it's a spawner, so it releases eggs and sperm during the day.
Okay, and so you're going to be doing this experiment on the spawning corals as well then?
Yeah, we'll be back in August to work on the elkhorn and staghorn corals.
I mean, broadcast spawners is what I suppose I meant, right? Okay, and then another question from the audience is, how many larvae get released from one colony typically?
Varies.
It varies quite a bit. I mean, so we have several that won't release any. We've had some that release 5. We've had some that release 1,500. So it varies a lot among the different colonies.
Does it matter how big the colony is or how small it is?
There is a slight relationship with size, but it's not a very big relationship. It's pretty kind of random across different size colonies.
Okay. You mentioned that you've done this experiment before, just not at Caribou. Do you have any preliminary results about the effects of ocean acidification on larval settlement, or do you have any hypotheses that you think is going to happen?
Yeah, so what we're doing is testing the combined effects of ocean acidification and seaweed contact together. So we kind of thought that ocean acidification would decrease settlement, exposure to seaweed would decrease settlement, but if you put the two together, you'd have a larger decrease in settlement. And so far, we really haven't found that. We've tested 3 different types of seaweed, and a couple of those types of seaweed seem to impact settlement some. We're not seeing huge effects of ocean acidification on settlement so far in our experiments.
Right. Yes, that's correct. So we don't think that OA will necessarily have a strong influence on this process of settlement. But after we actually conduct the settlement experiment, we also look at growth rates and survivorship of the tiny little baby corals for a week after we've conducted the settlement experiment. And what have we found? We found that there is a slight effect of OA on the survival of corals after the settlement process. So we don't think OA will have a direct effect on the process of settlement, but it might have a stronger influence on after the settlement stage when corals start to when corals start to grow out.
Wow. Okay.
It kind of makes sense because ocean acidification has some impact on the ability of organisms to calcify, and so as these little baby corals are growing, might influence their ability to calcify and grow, right?
Yeah.
Yeah, so that was going to be my next question. And so that's really interesting that as these corals are starting to grow from their very earliest stages, they need to lay on calcium carbonate, right? That's how they're built and how their skeletons grow. And then so that must be affected by the pH of the water. So interesting.
That's
Is that only with the one species of coral that you worked on so far, or is that true of other species?
The settlement results, you mean?
The settlement and or the post-settlement growth stuff that you're talking about.
So for our experiments, we've only worked so far on this one species of coral. I think there's been some work done that shows detrimental impacts to adult corals from ocean acidification, and then a limited amount of work on settlement and post-settlement survival.
right. So there has been a lot of empirical evidence that ocean acidification will decrease the growth rates of adult corals. And so, as Jenny mentioned, there isn't a whole lot of work that's been done on this settlement phase. And so that's why we're interested in looking at this particular life history phase of the corals.
Wow, okay. Thanks a lot. So I got one more question here for you, and this kind of wrap things up. The question is, what path, that is education, jobs, volunteer experience, etc., did you follow to get to your current position? And if you could make a suggestion for students interested in marine research or a career in marine research, what would you say to them?
Well, I'll tell you about my education path. I got a bachelor's degree in ecology and evolution. And after my undergrad degree, I had an internship at the University of North Carolina at Wilmington. I was a marine intern for about a year, and that position was actually more based down in the Florida Keys. And so I really got a lot of experience. That was my first hands-on job opportunity working in the marine environment, getting experience in coral reef ecology. And I did a lot of laboratory and field work during that year period. Afterwards, I then went to graduate school and I got an advanced degree, a PhD in biology. And after I graduated in 2012 with my graduate degree, I started a postdoc here with the Smithsonian. And I was a postdoc for about 2 years, and now currently I'm a staff biologist.
Any suggestions for students? And
I would say that the most important is to, of course, you want to find something that you're passionate about. This is a field that we are all in because we're really passionate about the organisms and the questions that we are pursuing. So find your passion and all enthusiasm.
Okay, thanks a lot.
so I started out, gosh, I guess I started out with a BS in biology. I was not one of those lucky people who always knew what they wanted to do when they grew up. So I kind of stumbled into a degree in biology and then decided to go back to grad school after about, I don't know, 9 months of working in an art gallery. And I came across chemical ecology as a field of study, and I thought it sounded really interesting. I really liked chemistry. I really liked ecology. So I kind of got into chemical ecology and then just happened to choose a master's project that involved seagrass. And then once I started working on seagrass, I got really interested in marine plants in general. So it took about 3 years after my master's degree. I taught high school, and then I went back for a PhD, and I got my PhD in chemistry in Germany, and studied bacterial communities on the surface of green algae and how chemicals that the algae produce affect the bacteria that associate with the algae. And so I kind of got into the microbial aspect of things, and then when I came to the Smithsonian, they were doing a lot of work on coral larval settlement stuff in association with a kind of algae called crustose corallin algae. And so I got really interested in the impacts of the microbial communities associated with the algae and how that might influence the behavior of the corals. So that's kind of where I started out at the Smithsonian as a postdoc in 2011. I started, and then I started as a staff biologist at the Smithsonian in 2012, in September of 2012. So here I am.
Okay, I
guess.
Sorry, I could share a picture of what you called CCA, crustose corallin algae, right? Just that pink, rosy pink stuff in that image there. Is that right?
I don't see a picture yet.
Oh, you don't see it? How about that?
I don't see anything.
Well.
Oh, wait, something's happening. Maybe. So it is, crustose corallin algae is a red alga that kind of grows like a paint. It looks like a paint on the surface of a rock. And a number of different kinds of invertebrates, marine invertebrates, use crustose corallin algae as a settlement cue. So a number of them like to settle on CCA, including corals. And so we use those a lot in our research. So when we're trying to settle out coral larvae, we often give them CCA as a substrate to settle on.
Okay. All right. Well, thanks a lot, you guys. That's about it for our time today. And thanks everyone else for joining in. A link to this archive video will be up on our YouTube page shortly. And yeah, thanks a lot, guys, and good luck with your final few days on the island. And have a safe trip home.
Hey, thanks,
Thank you.
Scott.
Bye.
Bye-bye.